So this is a topic within singularity theory. So let me recall what Lefschetz theorem says. It's one of the classical, one of the main theorems in algebraic geometry, and it's a fantastic theorem. So let V be a smooth, complex, projective variety of dimension n, and we consider the cohomology ring of the variety. And here J is the dimension. So the cohomology goes from 0 up to 2n, and we take omega, the cohomology class of the hyperplane section. And if we represent cohomology by the RAM cohomology, which means the closed differential forms modulo exact differential forms, then this cohomology class of the hyperplane section is a two cohomology class on CP2. This is J is equal to 2. Doing coproduct induces a map from the cohomology ring to itself. And in some sense, this organizes the structure of the cohomology. Lefschetz view this as if you take a cycle and you intersect with a hyperplane. So if a cycle has real dimension k and you intersect with a hyperplane, it will become a cycle of dimension k minus 2. And if you intersect with another hyperplane, it becomes a cycle of dimension k minus 4, and another cycle k minus 6. So in that sense, you begin with, you have your variety V, you intersect with a hyperplane, and so this gives you a codimension, complex codimension 1 subvariety of projective space. Now you intersect with another, so this is, so the thing is here, when we cup with H2, we're going to be moving in this direction. So this will be, you take H0, H2, H4, H6, and then you arrive to H2n. Now, here in H2, then one can consider the orthogonal complement. And so these will be the primitive cycles. These are the ones which do not come from higher dimensional things. And so the codimension 2 things are the ones, the hyperplane, and then it's complementary. So in some sense, here it's important to speak about the complementary. And then when you have these codimension 2 cycles, then you intersect with the hyperplane, and so you get codimension 4, codimension 6, codimension 8, codimension 10. And then when you arrive here at codimension 4, then you have the ones which is intersecting with 2 hyperplanes. This is the one which is intersecting this codimension 2 with the hyperplane, and then you have the new ones. So these ones over here are called the primitive cohomology. And so this is the basic cohomology, and then the rest are obtained by this process of cutting with a hyperplane. So now the wonderful thing here about this procedure, so here we make, I think in pictures. I don't think in formulas. I think that, when people give me some summation over J1, J2, less than, I tend to think that people don't understand. I understand with pictures. So this is my picture. So for me, the cohomology, there's something which will appear all over the talk is the following, is that since omega is a 2 form, there are 2 pyramids. There are even pyramids and odd pyramids. Because see, when you begin with, this is the manifold, then this is codimension 2, codimension 4, real codimension. When you cut with a hyperplane, it has codimension 2, real codimension 2. So when you cut a cycle with a codimension 2, you lower by codimension 2. So you have even and you have odd, and they don't mix together. And then in this process, you can see that cohomology will be, the H2 is bigger than H0, H4 is bigger than H2, then H6 is bigger than H4, and you arrive at the middle where it's maximal. And then it starts descending. There is this symmetry. And there are no holes over here. So these are not Egyptian pyramids with, I don't know how you call this, with tombs inside. No, no tombs. Here there are no tombs. These are solid pyramids, and this is represented by this fact. And so there are, so if you like what I don't like, here's an expression. See, Hj of Vq is equal to the direct sum of Lk. This is wedging with the hyperplane with the primitive one. So these are the fundamental ones. And then all the cohomology can be obtained by means of them. Now, as I mentioned, in this setting, it's important, what's important about cutting with hyperplane is that it's a nilpotent operator. If I keep repeating several times, I arrive at 0. So it's a linear map whose power, convenient power is 0. Now, also, there is a non-degenerate bilinear form between the primitive pieces. So here, so I made an example in here. So here we have, it's variety of dimension n. So this is n minus j, and this is n plus j. So if I do coproduct of something of dimension n minus j with something of dimension n plus j, I get something of dimension 2n, and then I can evaluate in the fundamental class, and so this gives me a bilinear form. But this is a bilinear form in two vector spaces, two different vector spaces. To really get you know, what we think of a bilinear form is a bilinear form in the same space. So what you do is the following. You get two elements here. One of them you push it over here, and then you do coproduct. And so this gives you a bilinear form. So what you do is you take two, then you push one of them to the other side, and then you do coproduct, and this gives you a bilinear form. And this is a non-degenerate bilinear form. And if you understand this is a non-degenerate bilinear form in the primitive pieces, you can construct all the bilinear form in all the manifold. So if one is interested in computing signature of the bilinear form, it's enough to know the signature of the primitive pieces, and then you just need a little combinatorics. So these are the fundamental pieces. So the basic ingredients for Lefschetz primitive decomposition is this a nilpotent operator and a non-degenerate bilinear form which satisfies the property that L is a symmetric or anti-symmetric operator with respect to the bilinear form. And this I learned from the analyst, that you have your Hermitian metric, and then you have a symmetric operator, and then you cook up another bilinear form by doing this kind of thing. So you can do this also geometrically. So this is coproduct, and this is cutting with a hyperplane. So we will see that this setting appears in other. Now, so that's the classical picture of Lefschetz theorem. No? Now, let's change the mathematical object. And so the mathematical object will be a germ of a holomorphic function with an isolated singularity in Cn plus 1. And so we can expand it into a power series. And so for me, the power series is the name. So it's different. Ignacio Luengo, the name, than the person. So many people don't like mathematics because they don't understand the difference between the name and the object. So, of course, So in that sense, this is the name, but this is the name of an object, of a mathematical object, of a beautiful mathematical object that we'd like to understand its properties. And so we will associate to this name first some topological considerations, which will be cohomological, then some algebraic, and there will be a relation between the topological and the algebraic, but the relation will be somehow mysterious. It is not true that because you can prove a theorem that A is equal to B, that you understand something. Sometimes A is equal to B, because if A was not equal to B, you do some argument and you arrive to a contradiction, but that doesn't give you any, okay, A is equal to B, but you would like to understand more. And so in that sense, we will see this appearing here. This is the classical approach to these two things. And in some sense, the modern part of the theory is where this differential aspect came into the theory, which is this D module. So this is a theory which is very well established, and I didn't learn it when I was in school. I had to learn it much later, and I've been taking some time to understand it, and I think it's a wonderful theory, but it's quite sophisticated. So now let's see the body. The body of the function is the decomposition of the ambient space into these disjoint fibers. This we learned in our analytic geometry course, and I think it was René Descartes, the one who invented this thing that, formulas have a body. So in that sense, when I write a function, I see, so first you have space, Rn or Cn, empty space. But when you have a function, then you have some capitalistic thing, because some are worth something and some are worth some other value. And so you have the set of points which have one fixed value. And then between having value, for example, if it's the sphere, sum of squares, x squares, then you have a sphere or you have a bigger sphere. And so in this case, this is a real picture. So one of them looks like this. Then the singularity looks like this. And then the other ones look like two copies of this. If you look near the boundary, they look just like two circles, and you cannot distinguish between who is the singular point and who is the non-singular point. And from the point of the boundary, you don't understand that there is a topological difference from going from the right to the left. So the implicit function theorem that we learned in school and that we teach it tells us the following information. So the body is a locally trivial vibration over the punctured disk by real 2 n-dimensional manifolds. We are in Cn plus 2. So the fibers are 2 n-dimensional real manifolds, complex manifolds of dimension n. The body restricted to the boundary of B is a trivial vibration by 2n minus 1 dimensional manifold, so it's just a product. And now here that it's a locally trivial vibration means like this. So I put this picture up to, so this is the fiber. Now when you go around, the fiber is transforming itself, and you come back to the same figure. Yes, but nobody said that you come back as the identity. So for example, perhaps one of the hands, you gave it a twist. And the neck, you gave it another twist, no? And so you come back, you come back to the same guy, but you never do nothing. It is never the identity. That's the point. It's not the identity. It's some map which is called the geometric monodromy. So when you go around the circle, so since we are complex functions, the values are the complex line, and the critical point is 0, So we remove 0, and so we have a fiber bundle over the punctured disk. And over the punctured disk, we have a locally trivial vibration, but the punctured disk, its first homotopy group is the integer, so you can go around. So when you go around and come back, you come back to the same guy, but you did something. That's called the geometric monodromy. Okay, so in particular to this guy, to this Da Vinci guy, you could have done some twisting. You twist. And so you're doing something. One would like to understand, what are you doing? You never do nothing. The only case where you do nothing is when there is no singularity. Every time there is a singularity, by force, you have to do something. Okay, so there is something to understand. So Milner in 1960 proved the theorem that said that taking small values of t and small values of z, then this fiber, the fiber, is homotopically a bouquet of mu n spheres. So this is a 2n dimensional manifold, which is a bouquet of mu n sphere. Bouquet means that these are just spheres which are held together by a common point. So what you can see in this description is that the only cohomology group which is non-trivial and interesting is Hn. H0, which is 1, but Hn. And so when you go around and come back, then you are moving around, you're getting a map. And it's not a map, it's not a simple map that this sphere goes to this sphere and this sphere goes, no. It's a more complicated map. It's a map between, so this is like a typical picture of how the thing looks. So that's the fiber, this V sub t. Now, we can consider these vector bundles. So we consider Hn the only interesting cohomology group, and we put it over the punctured disk. So for every point, for every value t, we consider the cohomology group of its fiber, and then it becomes a fiber bundle. So if we put rational coefficients, we could put rational or real or complex coefficients. It will become a vector bundle, and this vector bundle has a flat connection. So this flat connection is a reflection that if I have a homology cycle in the fiber and I move a little bit, there is a unique, so since cycles are with integer coefficients or rational coefficients, there is no way when you do a small perturbation to change things. So this forces that there is a connection, it's a flat connection, and it's called the Gauss-Manning connection, but really this is, Gauss and Manning had some previous results, but the one who got the real idea to consider is a Grothendieck's idea, and he was very generous to call it the Gauss-Manning connection because he could have called it the Grothendieck connection. So anyway, and so there's a monodromy map which goes from the cohomology group. So since we have a vector bundle now over the punctured disk, so we are changing the geometric picture where we have a geometric object into having a vector bundle where we have cohomology classes. And the geometric monodromy is transformed into a monodromy map, which is a linear map in cohomology. So now, there's the following problem, which is the following. See, when you consider the punctured disk, you might go around and see what happens when you go around. That's the classical problem of this monodromy. What you don't do, and people do now in the modern approach, is you don't go around. You tend to zero and see what happens. In Mexico, we would say, éntrale. No? No? Yeah, because you see the problem and you go around, no? And what happened? No, no, dice, no, éntrale, cabrón, no? So, no? in that sense, this classical point of view of just going around is a timid approach. One would like to really go to zero and see what happens. That opens a whole new kind of problems which were not studied classically, and which is the object which I'm interested in, and other people like Evelia were interested in these kind of things. So, and Manuel González Villa. So, when T goes to zero, the homology groups vanish, means that these homologies are going to zero, but they are not going to zero at the same speed, at different speeds. So, that's why, see, so here's this figure. Now, instead of going around, we're going to go to zero. So the thing is that the hands have to be coming out and the feet have to be coming out, but the body is shrinking. The body is shrinking. And then when you get to zero, all this body disappears, is crunched, and you're only left with the hands and the feet, okay? But now, nobody said that, you know, the face and the other organs are going down at the same speed. So there are two things to see. One thing is what happens when you go around and what happens when you go to zero. Now, the beautiful thing of complex variable is that, for example, the function t to the 1/2, when you go around, it changes by a sign because it has a square root. But also, it goes to zero at a certain speed. Now, t to the 3/2, when you go around, it also changes sign. Yeah, it changes sign, but not at the same speed when you go to zero, because t to the 3/2 goes to zero quicker than t to the 1/2. So both of them have the same monodromy, but you can distinguish them because when you go to zero, one of them is t to the 1/2 and the other one is t to the 3/2. So the modern theory is bringing this out. So as I mentioned, this monodromy, which is a linear map, as we all know, as we've been taught in our courses and we teach in our courses, when you consider a linear map, the important thing are the eigenvalues and the Jordan blocks. This is the fundamental thing of a matrix. And so the eigenvalues are going to call the eigenvalues of the monodromy, but when we try to understand the way things go to zero speeds, this will be something which is called the spectrum. So the spectrum of the singularity are some numbers, rational numbers, in such a way that e to the 2 pi I, these rational numbers are the eigenvalues. So it's an information which is finer than the eigenvalues, because if you do e to the 2 pi, the rational number, you recover the root of unity, which is the monodromy, but also it has an integer part. And this integer part, so it's a difference between 1/2, 3/2, 5/2, 7/2. All of them, when I do e to the 2 pi, they give me -1. But there's a difference. So in that sense, and also there's a problem which I cannot mention here because it doesn't give me time, but in some sense is one of the driving forces of of why I'm interested in this, is in the real problem, not the complex problem, the real problem. If instead of being on Cn+1, we are on Rn+1, because in that case, in the complex case, it's easy that only the nth cohomology group is non-zero. In the real case, there are several of the cohomology groups which are non-zero. But each one of them has a speed of vanishing, so they are grouped together by speed, and then what happens on the right and what happens on the left is related. So in the real case, so in the complex case, you have something, you go around, it's the same, and then you come back, it's the same on the right and on the left. But for the real numbers, you have to pass through zero, and then you come out and you have done one of these transsexual something, and then you become something else, you're something else, no? And so the thing is, how do you figure out what is on the right and what is on the left? And so there's a finer structure in the cohomology groups that one would like to understand. This is a completely wide open problem for the real case. So there's this classical theorem, this monodromy theorem proved by Briscorn that says that the eigenvalues of the monodromy are roots of unity, and that the size of the Jordan blocks of the monodromy have at most size n+1. Now, if you decompose the monodromy map as its semi-simple part times its unipotent part, it's the decomposition into its unipotent and semi-simple part, then this part of Briscorn theorem says that the unipotent part raised to the n+1 is equal to the identity. And now, what typically one does is you take the logarithm of the unipotent part. So you put mu minus the identity, that now becomes a nilpotent map. You raise it to the you do this sum, and then you're left with a linear nilpotent map whose exponential is the unipotent part. What we have done here is we have got rid of the distinction of the eigenvalues and we're just taking a look at the Jordan block decomposition. So the Jordan block decomposition is concentrated the information in this end. So this is a nilpotent map, and so this is the map that we're going to concentrate our information, because in this map there will be a filtration, so you can consider intuitively, you can consider the kernel of n, the kernel of n squared, the kernel of n cubed. You can do this, and then you get a flag. The link, one of the link's basic contribution to mathematics is that the basic object in mathematics is not a vector space. It's a flag in a vector space. So not all vectors in a vector space are the same. There's a flag, there's a distinction, and usually this comes into a family of subspaces that we will see that they appear. So the semi-simple part gives the orthogonal direct sum decomposition. I'm using the word orthogonal because, of course, I'm going to introduce a bilinear form in a second. And then, so this is the one which has eigenvalue 1, eigenvalue minus 1. And here I couple together eigenvalues and its complex conjugate. And so this gives me a decomposition of cohomology. And the unipotent part gives what's called the weight filtration. If n to the m0 plus 1 is 0, but n to the m0 is not 0, this is the order of nilpotency is m0, and this gives rise to a flag, a canonical flag in the space, which is reflecting one of the main objects I want to understand is what's the geometric meaning of this, and in particular, in the case of plane curve singularities, up to now, together with some collaborators, we have the idea that this is measuring the dent twist, the quantity of twists in the dent twists. So the n, so what's the information contained in the n? This is the unipotent part, the nilpotent part. And so the claim is that geometrically, in the case of two-dimensional surfaces, there are some twists. And so this n is measuring the set of places where you are having some twists. That separates. So there's a difference between speed of vanishing, which is measured by polar curves, and this n, it seems, is measuring some twisting. And this appears in all dimensions. So now, to introduce the bilinear form, we do the following thing. So we're going to introduce a non-degenerate bilinear form in vanishing cohomology. So you make an analytic change of coordinates so that f becomes now a polynomial, and that f equal to 0 defines a projective variety y0 in projective space which has an isolated singularity at 0. So you can do some local change of coordinate. You get rid of majority of you just left only with a polynomial, but this polynomial is non-singular everywhere except at the 0, and at infinity it's also smooth. So this means that the fiber f equals to t is going to be a smooth, compact, complex manifold of dimension n, and so we can consider coproduct there, and so we have a non-degenerate bilinear form there. So Hn of VTR has a, I'm sorry, so this YT is this projective variety for t different from 0, has a plus or minus symmetric non-degenerate bilinear form with orthogonal decomposition, and so it turns out that the eigenvalues, so this is orthogonal decomposition. You can do this thing for y, and so you get this thing, and then this is the cohomology on y. You have a monodromy on y. If you consider the kernel of n minus the identity, so these are the eigenvectors corresponding to the eigenvalue 1. If you get rid of these, what you're left is with the cohomology over here in Vt. And so what you do is that since this is orthogonal decomposition, you have this one, you transport it directly to V, this one you transport it directly to V, this one you transport it directly to V, and here you have to get rid of the plus 1 eigenvalues. The way it works is that you apply the n. Now, for me, it's still a mystery why this is the correct bilinear form, but this is the correct bilinear form. So this bilinear form, so here, this is coproduct. Everything is topological. Coproduct is topological. N is this topological. And so this is a form which is going to degenerate in the kernel of n, which is exactly the kernel of n minus the identity. So this, if you view it in Hn of Yt, is a bilinear form which degenerates over here, and so it is inducing a non-degenerate bilinear form over here. Now, the problem is that n is an anti-symmetric operator with respect to coproduct. So this means that this one, if coproduct was symmetric, when you put an n, it becomes antisymmetric. And if it's antisymmetric and you put an n, it becomes symmetric. So this becomes a bilinear form in Hn of VTR, which in one piece is symmetric and in another piece is antisymmetric, and you have orthogonal decomposition. They don't teach us in this linear algebra course either symmetric or antisymmetric. Here, naturally, it appears this form, which is mixed, and so this is the canonical form. Now, let me explain this thing about the pyramids. So, we're going to do this. This is how you get this flag, this flag corresponding to the nilpotent operator. So there's a canonical way to do it, but this canonical way to do it is very formal, and I don't understand it very well. I think people in general don't understand it very well, so I have a down-to-earth way to understand it, which is the following. You take, this is a Jordan block of size 1, 2, 3, 4, 5, 6. So you have another Jordan block of size 6, and you organize by Jordan blocks. And then you put this, and you organize as a pyramid. You organize them in the middle. And now, then the weight is, you're going to get this part, and then this part, and then this part, and then this part. That's the weight. You know, it's non-canonical. If you twist my hand and say, what's the canonical weight to a nilpotent operator? I say, the kernel of n. So see, the kernel of n are the guys which are in the end, because one more, they go to 0. And kernel of n squared are the ones which are 2, and then the ones which are 3. That's not the correct way. That's not the correct way. This is the correct way. Okay? And so this produces this weight. This is canonical weight associated to the nilpotent operator. And so you can organize this as being as pyramids, but now the thing is the following, is that if you have these blocks, the one which is on top has one less block. So this means that the pyramid is like bricklaying. You don't put a brick on top of the brick. It's halfway. Yeah, but then, and then halfway and halfway. This is how you do bricks, right? But then what you're going to do, so there is this degrading associated to the weight filtration. You know, we've all been taught in our algebra courses, you have a flag. Well, take the graded object associated to the weight filtration. Sure. You know what you do? You take these things and then you take direct sum. In some sense, you get a vector space of the same dimension, but the problem is that if this is representing cohomology classes, then the new objects are not cohomology classes. They are cohomology classes modulo another cohomology class. And so in that sense, it makes a difference. You know, when you take the graded object, you're not thinking now anymore about cohomology classes. You're thinking about principal parts of cohomology classes, which would be the leading term. So it makes a difference. And so then if you take the graded pieces, and then you can take the even, and then you get your pyramid, and the odd, and you get your pyramid. Okay? But so you always get 2 pyramids, even and odd. This has nothing to do with codimension 2, as I mentioned by Lefschetz theorem. This is a general fact about this flag. Now, if you write the bilinear form using these bases adapted to the flag, it turns out that the bilinear form has this form, and then you can see from here that these 2 are the same, these 2 are the same, and then here in the middle is a different one. And then the good thing about taking the grading is that bilinear form will only be a diagonal form. So why do you take the grading? If you're very practical, because it's a canonical procedure to get rid of the terms which are below the diagonal, okay? And then it becomes like an orthogonal decomposition. If one is interested in a signature, they have the same signature, so it's simpler to do the signature of this over this. Now, so if you carry the decomposition, primitive decomposition, then you can have a statement that tells you how your bilinear form decomposes into pieces. And what's important in this decomposition is the fact that these parts, when we're looking at signatures, will give us nothing, and these are the only parts which tell us where the signature is. So if you do, one can be technical and this. So this was the topology. Now I'm going to change things, talk about something else, which looks very similar, and then in the end, show the connection between the two. Okay? So the algebra associated to F. So we take now the Jacobian ideal of F in the ring of germs of holomorphic functions. So this is an ideal, and the Jacobian algebra is the ring of functions divided by the Jacobian ideal. Milnor showed that the hypothesis that F has an isolated singularity at 0, then this is a finite dimensional vector space, and that this dimension is the same dimension as the dimension of the cohomology group. So this gives an algebraic procedure that the computer can do for you to tell you what's the dimension of this group. Now, this does not give you a map between the algebra and the cohomology. It just tells you that the two vector spaces have the same dimension. Now, but is this an accident? Or what's the deeper, what's deep in here, no? Now, here we have multiplication by f in this algebra. This is an operator defined by multiplication with f, and we just multiply by f and g in the algebra. And so multiplication by f is a symmetric operator with respect to the algebra structure in AF, in the sense that if so it satisfies this property. It is nilpotent with index of nilpotency m0 n plus 1, which is a theorem of Skoda. And so that begins to resemble what we had in the other case. Now I can go quicker. We repeat the same process. Once we have a nilpotent map, there is a flag. So we have this flag, but now associated to multiplication by f. So here the question is, what's the relation between applying the nilpotent operator n, which is the logarithm of the unipotent part of the monodromy, and multiplication by f in the algebra? The two of them are vector spaces of the same dimension. The two of these are two nilpotent maps. And so the intriguing thing is, what's the relation between the two? So we do the same thing. Here these are the primitive parts. These would be the graded pieces. We form these pyramids. And now the bilinear form. This is a beautiful bilinear form, which is called Grothendieck duality. And it's a generalization of Cauchy's integral formula in several variables. And so it's good for any function with an isolated singularity. So you define a linear map, which is you take G, and then you compute the integral over gamma. Gamma is the cycle defined by the norm of Fj equal to epsilon of G divided by F0 up to Fn. So this gives you a linear map. And if G is in the Jacobian, is 0, so this gives you a linear map from the Jacobian algebra to the complex numbers. And Grothendieck bilinear pairing is defined in the following way. It's a map which goes from the algebra times the algebra to the complex numbers. You take two representatives, then you multiply G1 and G2, and you do this integral. And it's non-degenerate pairing by Grothendieck duality. If you apply this to the function c squared, you get Cauchy's integral formula. If you do this to the function c0 squared plus c1 squared up to cn squared, you get Cauchy's integral formula in n variables. You can do this for any function. And so the first time I met this in Griffiths-Harris' book, I said, what the hell? No, what's this? So it's a funny guy. So there's this bilinear form, and then you can repeat the same process. You can do primitive forms, then you can divide into pieces, organize the pieces. In the case that the function is real, you get some signatures. Everything becomes real, and so you have some signatures. And so there are many numbers which appear in this. Now, the thing. So now the thing is, what's the connection between the two? In principle, now you have two things which are similar, but if I ask, what's the connection between the two? You say, I don't know. It's not apparent. What's the relation between the cohomology groups of the fiber, of the smooth fiber, and the dimension of the Jacobian algebra? What's the relation between the nilpotent operator n, which is applied on the cohomology, and multiplication by f in the algebra? You know, they seem to be very unrelated guys. And so the relation becomes clear when you consider what's called the Brieskorn lattice. So the Brieskorn lattice are the following objects. See, there are two of them. This is differential forms on n plus 1, in Cn plus 1, divided by df exterior d omega n minus 1. So d omega n minus 1 is an exact n form, and you copy it with df, and you put this in the denominator. So this becomes n minus 1, d becomes an n, and then df becomes an n plus 1. So here you're taking differential forms modulo this. in here, you're taking df exterior omega n. So, see, when you do this, omega n can be written as sum of aj's dcj hat. So when you do df, you only get functions which are in the ideal generated by the partials of fj. That's a Jacobian ideal. Here, if you like exterior algebra, you see this is the Jacobian ideal. And so when you take the quotient of this by this, you get this space, which is this space, which is isomorphic to the Jacobian algebra. It's called the Jacobian module. So this means that here it appears the Jacobian algebra. Now, this is not an object in algebraic geometry. Algebraic geometry, as was taught by Serre and Grothendieck, it's a theory about O modules. The omega n minus 1 is not an O module. So when you do this division, you have to do this division as vector spaces because it's not an O module. So at the moment that we do this, if you're a straight algebraic geometer, you're out of the game. This is not an algebraic geometric object. So this is So now, consider the cohomologic bundle over the punctured disk. Here we're pushing forward. So what we're doing is we have this bundle, and over here we have this Hn. It is a mu-dimensional flat vector bundle, as I explained, over the punctured disk with the Gauss-Manning connection, whose fiber over T is these vanishing cohomology groups. Now, this bundle has a natural invariant non-degenerate bilinear form obtained by gluing together each of these. And we denote by Hn bar the germ at 0 of the holomorphic sections of this bundle. Now, there's a temptation to put on the bundle a fiber and extend you can do it in general, to do an extension, but we are not going to do this. We don't want to put a fiber over 0. We want to do something else. And so this something else is the following. So, we're going to define a map from n differential forms to Hn. So this is from n differential forms in the ambient space to sections of the bundle. And so what you do is you take the n form, you restrict it to the fiber, and you take its cohomology class. And a holomorphic n form restricted to an n manifold is always closed. So it gives you a class. So this gives you some sections of the bundle over the punctured disk. Here we're doing it over the punctured disk. So restrict the n differential form to the n-dimensional manifold, which is a closed form, and then take its cohomology class using the RAM cohomology. And so this is the map. Now, if you do df exterior with sigma, but if you have df vanishes on the fiber. So this is 0, so this is identically equal to 0 because it's tangent to the fibers. So this is 0. And then if you do S of a closed form, then you say, well, if this is globally closed in Cn plus 1, when you restrict to Vt, it's still a closed form. So when you take its cohomology class is 0. So this means that this map is going to be 0 in everything which we can factor a df, and is going to be 0 on the closed forms. And so, there's the RAM lemma, and so this means that this S will be a function which is defined. So this is, if you take a form of the form df exterior with something, then this something is the one you restrict, and this gives you the map. And what you have done with this is that if you're in the kernel, so if something is in the kernel of this, because you have an element here, you're lifting it here. So if you choose another lifting, it differs by a guy over here, but then I just mentioned that this guy is 0. So this means that there is a map from this H0 prime into Hn. So this means that we're getting some specific sections of the bundle which have a geometric meaning that when t tends to 0, they are not going to infinity. So this means that the way we are, we're not putting a fiber over 0. What we're doing is we're getting some special sections which come from Cn plus 1. And so these are these ones, and then we can, we can extend this map to this other one, which was a little bit bigger, which is by the following trick, to obtain some holomorphic sections that we call admissible. The other ones we call trivial, these ones we call admissible. And the trick is the following. So you do F, so you take a certain form of omega. So first of all, is if you take FL times something, it will come out as a T, because since you're restricting to the fiber, if you multiply by F, it's the same as multiplication by T. And so if you take a form omega, you can multiply by a power of F, and then you can write it in this form. And then you define S of omega, and then you pass this T to the minus L to this other form. So this means that the previous formula works. The only thing is you have to multiply by a power of F, and then you divide by a power of T. And so this gives you the extension. So this can also be done using Poincare residues. And so this means that we have an isomorphism from admissible sections modulo trivial sections into this omega F. And so invariants on the left are the spectrum that I said are some precise way of getting logarithms of the eigenvalue. And then to every n-Jordan block of size m, we're going to get a family of these points in the spectrum, lambda, lambda plus 1, lambda plus m. And then to an F-Jordan chain, we can associate several of these n-Jordan chains. And then we put one of these first n-Jordan chains, we put the other one, and then these are related one by the other. So in that sense, the F chains are obtained by gluing together n chains. And so that's why I said that this gives an answer to this problem. And then there's also a procedure to construct the primitive forms by gluing primitive n forms with some additional bilinear forms. And so that's this picture. This is more or less the answer to this question of the relation between F chains and n chains. And one passes through some Laurent series expansion. But I think I'm going to stop here.